Let's continue now. Before I talk about unique factorization domains and principal ideal domains, which is going to be our goal for the next few videos, let me correct something I said in a previous video which was incorrect. Okay, so let me, this is the correction. So this is a correction that I want to make, and the correction is it's something where I made a remark that I made in passing. So recall that we know that the polynomial ring in one variable over Z is Noetherian. We definitely know that because we can use Hilbert basis theorem, right? Hilbert basis theorem, recall, which we proved last time, says that if you have a Noetherian ring, this says that R Noetherian implies Rx Noetherian. So the polynomial ring in one variable over a Noetherian ring is also Noetherian. We certainly know that the ring of integers is Noetherian because every ideal in Z is actually principal, so finitely generated. So Zx is Noetherian. The mistake I made was when I said that every ideal in Zx is generated by two elements. So the statement now I want to, it is not true that every element of Zx generated by two elements. Okay, so this is something that I said in a previous video and I actually asked you to do as an exercise that statement so that you know that Zx is Noetherian without using Hilbert basis theorem. But this is not true. Okay, so in fact there are elements, there are ideals, sorry, I should not say element. It is not true that every ideal of Zx is generated by two elements. That's false. In fact, there are ideals in Zx that are generated by three elements and that cannot be generated by two elements. In more generally, and we have in fact for any n, there are ideals of Zx that are generated by n elements but not by n minus 1 elements. Okay, so as an example, this is something that I cannot prove. It requires some more techniques in ring theory to prove this. So I'll only assert this. You can think about this some other time. So if you take the ideal generated by 4, 2x and x squared. Okay, so certainly I is generated by three elements by definition, by 4, 2x and x squared. I is not generated by less than 3 elements. So I is not principal, which is not difficult to show, and but I is also not generated by any two elements. So that you take, there are no two elements in I that generate I. That's what I mean. You need at least 3 elements to generate I. So as I said, this requires some techniques that we are not going to cover in this course, but it's something for you to keep in your mind. Remember that the fact that Zx is Noetherian is still true. We do not need the stronger statement that every ideal of Zx is generated by two elements. We only need the statement that every ideal of Zx is finitely generated. I is in this example certainly finitely generated because it's generated by 3 elements. I am saying that it is not generated by less than 3 elements. Okay, so that is just a correction I wanted to make about Noetherian rings and this example that we discussed in a previous video. Okay, so the next goal for us is to introduce next topic in the course is what are called principal ideal domains and which I will denote, which is very standard notation, is called PID, principal ideal domains, and unique factorization domains. So these are called UFDs. So these are the abbreviations. So these are special kinds of rings. So the rings which have certain nice properties, and we will discuss these in this video and next 2 or 3 videos. Okay, so before I start talking about these exact properties of these rings, let me introduce some generalities. So some general stuff. So in today's video and in next few videos, we will work with only integral domains. Okay, so many of the concepts that we will introduce are valid only for integral domains, and the reason we do this is principal ideal domains, unique factorization domain, as the word domain suggests, they are actually integral domains and with additional properties. So we are going to stick to integral domains. So let us start with this. Let R be an integral domain. As I am going to do these concepts that I will introduce in today's video, keep in mind the example of the integers. All these concepts are actually developed with integers as the model. So we look at the nice properties that integers have and try to generalize them to more rings. Okay, so in this process, let me give some definitions. Okay, so these are just definitions or notations. So we say that, so let A and B be 2 elements of R. Okay, so let's say A and B are 2 elements of R. We say that, so this is very common language, but I want to formally define this so that in future it will be clear to you. We say that B divides A, or B is a divisor of A So we are familiar with the notion of division for integers. So I am trying to generalize this to an arbitrary integral domain. We say B divides A or B is a divisor of A if the most natural thing, right? BC is equal to A for some C in R. So if A is a multiple of B, we say B divides A. This is of course what we mean when we say 3 divides 12, right? 3 divides 12, that means 3, that is because 3 times 4 is 12. So that's now generalized to an arbitrary ring situation. And we use a notation, this is convenient, instead of writing in words B divides A, we write B divides A. To indicate that, we write B vertical bar A. This implies this is a shorthand for the statement B divides A, that I will use often. Okay. Or that B is a proper divisor, P is a divisor of A. On the other hand, we want to introduce the notion of a proper divisor. We say that B is a proper divisor of A if, of course, first of all, B divides, if BC is equal to A for some C and neither B nor C is a unit. Okay, so this is an important notion here. So let me explain this. First of all, in order for a proper divisor, in order to be a proper divisor, it must be a divisor. But I want to rule out certain obvious divisors. I don't want to consider those trivial divisors. So I am introducing the notion of a proper divisor. What do I mean by a proper divisor? I first of all want B to divide it, so BC is equal to A, but I don't want C or B to be a unit. Recall that a unit in a ring is an element which has a Remember what is a unit? It is an element which has a multiplicative inverse. Remember, in a ring, not every element is required to have a multiplicative inverse. If it does have a multiplicative inverse, we call it a unit. Okay. So this is in order to be a proper divisor, first of all, it cannot be a unit, and what it multiplies to cannot also be a unit. So as an example, we can say 2 is a proper divisor of 10. Right? In Z, of course, this is an example is in Z. 2 is a proper divisor of 10 because 2 times 5 is a 10 and 2 and 5 are not units. What are units in Z? It's clear that the only units in Z are the integer 1 and the integer minus 1. So 2 is a proper divisor of 10. On the other hand, 1 is not a proper divisor of, it is a divisor, all right, but it's not a proper divisor of 10. Right? This is because 1 is a unit. A proper divisor cannot be a unit. So on the other hand, minus 10 is also not a, minus 10 and 10 are not proper divisors of 10 also, right? Because 10 times 1 is a 10, but this is a unit. Similarly, minus 10 times minus 1 is a 10 and this is a unit. So 10 and minus 10 are actually divisors of 10, but what you multiply them with to get 10 is a unit. So 10 and minus 10 are not proper divisors. 1 is not a proper divisor. So 10 has several divisors, but only some of them are not proper, some of them are proper. So this is a general notion. In general, in any ring, we have the notion of a proper divisor. One more definition, we say that two elements A, B in R. So now I am back to an arbitrary integral domain. Remember that I am not working with an arbitrary ring in this video, I am working with an arbitrary integral domain. We say that two elements A, B in an integral domain are associates if A is equal to BU for some unit U, or equivalently A and B divide each other. Okay, so associates means A divides B, B divides A. Of course, every element is an associate of itself, but there could be two different elements which are associates of each other. For example, 2 and minus 2 are associates in Z, right? 2 is minus 2 times minus 1 is a unit, so they are associates. 2 and 3 are not associates. 2 and 4 are not associates, right? The only associate of 2 is actually 2 or minus 2. So in Z, this is what happens. In let's look at another example now. R equal to Zi. Remember, Zi is the ring of all complex numbers which are of the form A plus IB, where A and B are integers, and this is an integral domain. Being a subring of a field, it is an integral domain. So we can also talk about associates in this ring. And what are units of R? I don't recall if I explicitly did this, but I mentioned this I think sometime in the beginning of this course. Units of Zi are actually there are 4 of them. 1 minus 1 I minus I. So these are the units of this ring Zi. So now in using these units we see that so 1 plus I and I minus 1 are units, are associates. Why is this? This is because I minus 1 is 1 plus I times I, right? I is a unit, this times a unit is 1 minus I minus 1, so they are associates. Similarly, 2 plus I and 1 minus 2I are associates. Okay, because 2 plus I times so let's see, 2 plus I times I or minus I. Minus I is also a unit. When you multiply 2 plus I and minus I, you get minus 2I plus 1, which is equal to that. So these are also associates. So this example shows that associates may look different. In the familiar example of integers, of course, an associate of a number is either that number or the negative of that number. But if a ring has more units, you have more interesting associates. So these are examples of associates. Okay, so now we have defined what it means for an element to be a divisor of another element, what it means for an element to be a proper divisor of another element, and we also defined the notion of associates. So now I am going to give you 2 very important definitions which are valid in any integral domains. Okay, so what are these 2 important definitions? 1, so let R be an integral domain. So I'll shorten it like this. Let R be an integral domain. So I want to define the following 2 things. So first I will say that, and let A be an element of R. Okay, so we say that A is irreducible. So we have talked about irreducible polynomials earlier, and this is actually same as that, but now I am doing this not just in any polynomial ring, but in fact for any integral domain. A is irreducible if the following happens. What do you think it should happen? Remember, irreducible polynomials are those that do not factor in a non-trivial way. So same notion I will use. A is irreducible if I want first of all that A should not be a unit. I don't want to call units irreducible for simplicity, because I don't want to, every time I'm working in a proof or something and I'm working with irreducible elements, I don't want to assume that it's not a unit. So I'll declare that an irreducible element is by definition not a unit, and it has no proper divisors. Right? So if you think about this, this is exactly what we have in the case of polynomial rings. A polynomial is irreducible if it really has no proper divisor. Remember, everything has a divisor because A is a divisor of itself. Any unit is a divisor of A. But I don't want to consider those as actual divisors. So I will only ask that it has no proper divisors. Then it is irreducible. I will give you examples and discuss more about this after giving both definitions. So the other important definition is A is prime. So the other important definition is A is prime. Again, if A is not a unit, so I again do not want to consider units as primes, and if A divides a product BC, where of course B and C are elements of R, this should recall for you the definition of prime numbers in integers. So if A is not a unit and if A divides a product BC, then A divides B or A divides C. Right? So This is what we call a prime element. A prime element is one which is not a unit, and it has a property that if it divides a product of two elements, two other ring elements, it must divide one of them. So now let me quickly give you some obvious examples before we discuss more interesting examples. When R is Z, these two notions are same. What I mean is, an integer, if A belongs to Z, A is irreducible if and only if A is prime. This is something that you may have studied in, you may remember from some high school arithmetic that you may have done. See, prime numbers, of course, we know. It's one definition of prime number is that what we are now calling irreducible is often what people think of as prime integer, because a number, an integer is prime if it has no factors other than 1 and that integer. But 1 and that integer in our notation are proper divisors. So you take a positive integer, we call it a prime if it has no other positive proper divisors. It has no divisors other than 1 and p. Then p is prime. That notion is actually what we are calling irreducible in the case of an arbitrary integral domain. But you also do, after defining prime numbers, the theorem that a prime integer has the property that if that integer p is prime, if and only if p divides a product of two integers a and b, then it must divide one of them. For example, 5 divides ab, this is something you would have seen before. Then 5 divides a or 5 divides b. This kind of statement you see in, this kind of statement is familiar to you. 5 is prime because it has this property. That is what we are calling a prime element in an integral domain. In the case of the integral domain Z, these are actually same. Irreducibility is equivalent to primality. So, what are irreducible elements of Z? I mean, you can write, 1 should not be considered irreducible because 1 is a unit. So, there are 2, 5, 2, 3, 5, 7 and so on. And of course, we can also consider, nothing in the definition disallows these also. Negatives of these are also prime elements or irreducible elements. Okay, so in the case of Z, it's very clear that they are both the same concept. An element is irreducible if and only if it is prime. So now on the other hand, so this is, as I said, a familiar example. Now let's look at the ring R equal to Z adjoined square root of minus 5. Now this ring is very similar to Z adjoined I in the sense that it is all complex numbers which are of the form a plus b times square root minus 5 where a and b are integers. So this is a subring of C. So R is an integral domain. Okay, so R is an integral domain. So in this, I want to introduce, I want to actually show that there is an irreducible element that's not prime, which that phenomenon does not happen in Z, because every irreducible element is prime, every prime element is irreducible, but that is not in general true. So in this I make two claims. 2 is an element of R, is irreducible, but 2 is not prime. Okay, so this I'm going to prove these two statements. So I'm claiming that the element 2 in the ring R, which is Z adjoined square root minus 5, is irreducible but not prime. Okay, so in general, in other words, irreducible elements need not be prime. So first of all, why is 2 prime or not prime? So let's prove that first. 2 is not prime. Okay, the remaining part of this video will be proving this claim, which is not difficult, but it's a tedious calculation. So please make sure that you carefully follow this. This is an interesting example that we will encounter again in the course. So 2 is not prime. What do I need to show that 2 is not prime? I need to show that there are two elements in the ring whose product 2 divides, but 2 does not divide it. So, and the product that I will take is 6. So 2 divides, I claim 1 plus root minus 5 times 1 minus root minus 5. What is 1 plus, so this is my B if you want, and this is my C. What is 1 plus root minus 5 times 1 minus root minus 5? This is the usual formula, right? A minus B times A plus B is A squared minus B squared. So this is 1 squared minus square root minus 5 squared. So this is 1 minus minus 5. This is 1 plus 5, which is 6. So certainly 2 divides BC. So 2 divides BC. We will show now that 2 does not divide B and 2 does not divide C. Right? If 2 divides the product of B and C, but 2 doesn't divide B or 2 doesn't divide C, then by definition 2 cannot be a prime. So why does not 2 does not divide, why doesn't 2 divide B? The reason is, so suppose 2 divides B. So we'll proceed by contradiction. Suppose 2 divides B. What is the meaning of that? At the beginning of this video, I told you in general in any ring, when an element divides another element, I mean that 2 times some ring element is B, right? 2 times a ring element is B. In this case, in the 2 divides 6, because 2 is, of course, 2 times 3 is 6. So 2 divides 6. So 2 divides B, remember B is 1 plus root minus 5. If 2 times some x plus y square root minus 5 is equal to 1 plus root minus 5, where x and y are in Z. If there exist x and y integers such that 2 times x plus y minus y square root minus 5 is equal to 1 plus square root minus 5, then we say 2 divides 1 plus square root minus 5. So I am going to show that this is not possible. So let's see some consequences of this equality. So you have 2x plus 2y square root minus 5 is 1 plus square root minus 5. So I am going to rearrange terms here. I will subtract 1 and write 1 minus 2y times square root minus 5. Right? So I am pooling together the like terms. 2x minus 1. So 1 comes here, 2y square root minus 5 goes there. So I have 1 minus 2y times square root minus 5. But now I can work inside the complex numbers. These are all complex numbers. In other words, I can divide by 1 minus 2y to do this. First of all, 1 minus 2y cannot be 0 because y is an integer. Remember, y is an integer. That means 1 cannot equal to y. 1 is an odd integer, in other words. So 1 minus 2y cannot be 0, so I can divide by 1 minus 2y. But this is absurd. Why is this absurd? For several reasons. One reason is that this is a rational number, right? Because it's a ratio of 2 integers, it is a rational number. Certainly square root minus 5 is not a rational number. Also, this is a real number, but this cannot be a real number. So that's another reason. So 2 does not divide B. So do you agree that I have proved that 2 does not divide B? Similarly, 2 does not divide, right? So I hope this is clear to you. So the same proof more or less, you assume that 2 times x plus y times x plus y square root minus 5 is equal to 1 minus square root minus 5, which was C, and do similar calculation to get a contradiction. So 2 does not divide C, 2 does not divide B, but 2 divides BC. Hence, 2 is not prime. So this is the first part.